Okay, perfect. So
Thursday?
this is going to be the same one as Thursday. So remember how we do Thursday and Sundays of each like session. Those will be the same.
Mm-hmm.
So this will be the same review, but obviously like if there's different questions or whatever, we'll have that. So all right, cool. So let's do, if I can find this. Oh, all right, here we go. Cases and variables. So we're gonna do lesson 1. So if I didn't introduce myself, I'm Anne Marie. I'm a senior at Penn State. Super fun. I'm really sad. I don't want to be a senior, but I took STAT. I've been doing tutoring for like 4 years for this, so hopefully I know what I'm doing. So let me know if you guys are confused. Okay, yeah, no, thank you. I appreciate it, Jimmy. Yeah, if everyone could just put their email in the chat box, we just use it for just attendance purposes so that we can keep you know, doing these things for free. Everyone likes free things. Okay. So let's talk about cases and variables. So these are kind of like our basis of statistics. Cases are kind of the overarching what we get after we collect all of our variables. And we also call them units, experimental units. So it's just what we use when we collect all the data, and those are the specific things that we use. Our variables are going to be the different things that we measure, but these are the ones that, like, it comes from the name, they are variable, they change. So it's different from like constants, they stay consistent. Variables are going to change. And so we have 2 different types of variables. We have categorical variables and quantitative. So we have our categorical variables, which are labels and groups, and then our quantitative variables, which are going to be involving numbers and actual values. So for categorical variables, they aren't really attached to a value on the number line, excuse me, but for quantitative, they do have some sort of value attached to them, like within numbers. So categorical, we can have nominal or ordinal. So nominal are just going to be categorical variables that can take on any order. They can be things like colors, flavors of something, brands, what else? Types of clothing, that kind of thing. And then we have ordinal variables, which they're still categorical, so they still are just labels or groups, but they have some sort of hierarchy to them. So I often use the example of like class ranking, so like freshman, sophomore, junior, senior, anything that involves being, or like maybe like bronze medal, silver medal, gold medal, you know, they're still categorical because like they're colors, types of medals, whatever, but they have a hierarchy to them if you're like doing it in regards of like the Olympics or whatever. So those would be categorical variables. Then for quantitative variables, we have 2 different types. We have discrete or continuous. Our discrete variables mean that they only take on a set number of values. You can't choose just any value on the number line, so that can be anything from like people, like things you can't cut in half. So hopefully you aren't cutting people in half. Or so like cars, streets, that kind of thing. I guess some like, I don't know, maybe not streets, but just things that can only have a set number of values, when in comparison to continuous variables, they can have any amount on the number line. They can take on any value. So these can be things like we can have weights, heights, any type of measurement is usually in this realm. So anything like pounds, inches, centimeters, any of that. Because as you know, like when you have like a measurement, you can really choose any measurement on that line. It doesn't have to be the specific, you know, it doesn't have to be 1 inch, 2 inch, 3 inch. It could be 1 1/4, you know, 3 3/8. So that would be continuous. Alrighty. Okay, so continuing on to like variables, we have 2 different types of variables when we're talking about in regards to how they interact with each other. So our explanatory variables, as the name says, they explain our response variable. So So yeah, they explain our response variable. They're the variables that are independent, so they're not really affected by anything. And then we have our, oh, I found my pen. Okay, whew, got it. Okay, so our explanatory variables are going to be the independent ones. So they stay constant. They're static. So, and the reason why is because if they weren't, they wouldn't be able to accurately explain that difference in our response variable, which is our outcome variable. What else? So yeah, like I said, we have our explanatory variable, which is going to be our independent variable. So it doesn't change. It's not affected by anything. And then our response variable is dependent on that explanatory variable. So depending on what happens to the explanatory variable, the response variable will reflect that and will change in regards to that. And then just to go a little bit more in depth about independence and dependence, because sometimes those are terms that are kind of tricky. So independence, if two things are independent from each other, they're not related to each other. I always say, you know, if you're independent, you don't need no one. You know, you're unrelated to each other. So, you know, that's an example when you're talking, and these usually come from randomized experiments, because if you randomize something, then it doesn't necessarily have to, that's going to make sure that they don't have any connection to one another. So that's examples for that. And then dependence means that they can affect each other. We use, like, often we have paired or matched pairs, and that's going to be when we have the subjects and often the subjects are the same in both groups, because if they are, then obviously what happens to those individuals in one case is going to affect them in the other case, because they're the same individuals. So the different variables that are impacting them will impact them in the second situation that you have going on here. So I always use the example of if you're comparing quiz scores to exam scores. So let's say you take a class and you have a class and you first take all their quiz scores and then you compare them to their exam scores to see if there's a correlation there. That's an example of like paired, and that's an example of the subjects being the same in both groups and how they're dependent on one another. Because theoretically we're saying like your quiz score is going to affect your exam score. So like how well you do on the quiz for that subject may reflect how well you do on the exam for that subject. So that's just an example there. Okie dokie. Let's see. Okay, samples and populations. So this is another important thing to wrap your head around for statistics, because this kind of shows like where we get our samples from, you know, why, you know, one is variable, one's not, why our populations are fixed. So I kind of drew this in the way that, right now I have to figure out how to annotate again. This is, oh, I can change the color. That's nice. Okay, so I was trying to write on my board and I didn't plug it in. Oh, okay, don't worry, everyone. Okay, so we have our samples and populations. So, for example, our populations are going to be our fixed group. These are going to be the whole group that we're looking at total. So, for example, we can use like the U.S. Census. That can be something that's our population, because that's showing us like the population of America or whatever. They're fixed, and because they have to be fixed so that when you take samples out of them, you're taking like samples that are going to be representative, because if it's not fixed, then that's going to change every time you take a sample, and you're not going to get you know, accurate responses. And then from our populations, we get samples. So our samples come from these populations. So our samples are going to be the group that you take from that population, and then since it's hard to collect data specifically from populations, we use these samples for collecting the data. So we take that sample, and then within that sample is where we're going to get the data. And these ones are variable, because usually what you want to do is take a random sample so that there's no bias in that case. So it's obviously going to change every time. And then we use that sample to make inferences about the population. So the way I look at this is kind of in a cycle. So we start with our population, and we take out a sample, and we get the sample. And then we take this sample, to make an inference about our population. So I'm very visual. You'll see I like to use a lot of color coding and stuff as we go on. So like I said, yeah, I kind of use this as a sample, you know. So we first have our population up here, and then we take a sample from that population. We end up down here with our sample, and then we use whatever sample we got to make an inference about our population. Because we can't, it's hard to take samples of a population completely total. So that's something to keep in mind there. You know, it would be hard to ask every American a question that you're trying to find out about America. So that's why we take these samples out, because it's more, that's like more feasible, and that makes more sense to take samples or information from a sample. It's a little bit easier to do. Okay, so let me clear. I need to do this. Clear all drawing. Okay. Oh snap. All right, here we go. So we have different sampling methods. So this is what we were just talking about when you take samples from the population. These are different methods that you could use. Commonly, simple random sampling is used. This is just talking about taking a sample from that population without replacement. So you'll take a sample, and then you'll take another sample from the population, and then you'll take another sample. And saying it without replacement means that if you had a sample of 200 and you took, or let's say your population was 200 and you took a sample of 50, then the next sample you take out of there will be from a population of 150, because you're not replacing that 50 that you just took. And it's probability based. It's just saying there's an equal probability of selection for each individual unit in that sample. So yeah, the simple random sampling. And then convenience sampling is not really a preferred method. Often it's used if you don't have access to the entire population. You just kind of use it when all you have is kind of what you got, and you got to work with what you have. So it's easy to do. It's using the easiest way you can do it. Like if you're trying to find information about all classes at Penn State, but you only have access to the one class that you're in, that would be convenience sampling. You're only asking one class, and it's not going to be random. It's not going to be representative, because you can't assume that the things that you have conveniently in front of you are going to represent your entire population, which is what we want in a sample. We want our samples to represent our population in order to make accurate inferences about that. All right. Okay, so we want to make sure that we don't have bias. Like I was talking about, we want that representative sample. If we don't, we can have bias going on there. So yeah, if it's representative, it means it's representing our population, which is what we want. I kind of just said all that. And we don't want to have sampling bias. So sampling biases would be that we're taking samples out and it's favoring certain outcomes. So this is things like if people don't respond because they're not interested in the topic, so then you're only going to get responses from people interested in the topic, which can skew your data, make it, that's going to be biased towards people interested in the topic. This could be things like if people do respond, but they're responding in a way that they think they should. I use the example of if a teacher is surveying their students on if they ever cheated in their class, their responses are probably going to be no, if they don't want to get in trouble type thing. But so that response is favoring a certain outcome that may not be truthful, because maybe a lot of them did cheat, but they're saying no because they don't want to get in trouble. So that's another example of how we could get bias in that case. Okay, just another thing. This is just a main point to keep in mind. Causation does not equal association. So just because one thing is associated to another, just because you make an inference and you see this thing is associated to this thing, that does not mean that they cause one another. Especially if this is important in observational studies. If you're making observations and you figure out that there's an association between one variable to another one, you can't say that one causes the other. Like I said, especially in observational studies, which we'll talk about next, because you didn't impose any sort of treatment on there. So in reality, it could be coincidence. So we don't know that because we didn't control for anything there. So, but if we have a randomized experiment, we can make causal conclusions. So this would be more like experiments, not observational studies. So we would be able to make conclusions in that case about causation, but the main point is that just because you find that there's an association or a relationship between two things, you can't make a claim that one causes the other. So without randomization, you can say there's an association, but you can't say that they cause one another. See, if I sound like I'm repeating myself, it's because it's an important point to remember. So, okay, let's see. So yeah, like I said, we'll talk quickly about observational experimental studies. So experimental studies are going to be the studies that we impose some sort of treatment on. The researcher is putting something, they're changing something of the participants or the variables within it in order to study it. Call it a scientific study because, in science, usually you're imposing some sort of treatment to, manipulate the variables and then see how they reacted, like how they change in that aspect. So yeah, and this is how you can control for confounding variables if you randomize the experiment. So randomization is always a good idea. A confounding variable, to review that, it's just a variable that's related to your other variables, but it's not what we're studying. So it can be affecting your variables, but it's not exactly what we want to be studying. We don't want it to be affecting us in that, like we don't want it to be affecting the variables in that way. So to control for this, you can do a randomized experiment. So this is making sure that there's no bias going on, there's no confounding variables because you're just randomizing it, so that should kind of even the playing field in that case. Observational studies are just ones where there's no manipulation going on. The researcher is just observing what's going on. If let's say they're observing like rats in their natural habitat, they would literally just watch them and take data on them. So that's all that would be. But this does run the risk of confounding variables because, like we've been saying, there's no sort of randomization in observational studies, kind of hands off, just watching what's going on. And since there's no randomization, we could have confounding variables. And also remember, for observational studies, I'll just add here, if I can figure out how to annotate. So we can't make causal relationships. So this is just something to keep in mind. So remember, if we are just observing and there's no manipulation and there's no randomization, then we can't make those causal relationships. Okay. Okay. So when you're doing an experimental study and imposing that treatment upon the study, you can use a control group. And this is basically your group that's receiving no treatment at all. So your control group receives no treatment, and then a type of control group could be a placebo group where they're receiving a fake treatment. So they're receiving a treatment, but it's not real. So technically they're not receiving treatment, but it appears that they are. So if you're studying people and like how medicine works, maybe you give each group medicine, but one group receives medicine that doesn't do anything. It's a placebo pill. Blinding is what ensures our validity upon this. So we want to make sure that, so like for single blind means that the participants don't know what treatment group they're in. So using the example of the medicine, they don't know if they're taking the placebo or the actual pill. And then double blind helps with researcher bias. So this is important if the researcher has background in the subject and like they could possibly be biased when they're choosing the groups. So double blind, the participants don't know. They don't know which group they're getting into. And double blind means both the participants and the researcher doesn't know. So the researcher has no clue which group is getting the placebo and which group is getting the actual pill. So, okay, yeah, that's about that. Okay, so we'll do some review questions now. So the way we do these is basically we just kind of go through and I'll read the question. You guys can check out the answers and pick what you think it is. This is a safe space. Answer what you think it is. If you don't know, we'll go over it together, like no matter what. So take your best guess, and we'll review all of them. So I think we have 1, 2, 3, 4. We have 4 of them today. So we'll go ahead and go through these and see what you think about them. So, all right, so we have a research question. So do 6-month-old babies who are being breastfed weigh more than 6-month-old babies who are not being breastfed? So data were collected concerning 10,000 6-month-old babies. Whether or not the baby was being breastfed was recorded, as well as the baby's weight in pounds. So which of the following statements is true about this study? So go ahead, read through these options, and let me know what you think is the right answer. No, you can still answer. That's totally fine. That's totally fine. I don't mind. But if you want to, that's fine too. Or yeah, but okay. So good job. This answer is B. So we'll just kind of go through and talk about why it isn't the rest of them. So for A, it's saying it doesn't have a large enough sample size. This isn't true. We do have a large enough sample size. We have 10,000. I don't know if you guys learned yet. N is how we represent sample size, so N equals 10,000. So A is not correct. For C, it's saying the group being breastfed is the placebo group. That's not true, because remember, placebo group is like not receiving treatment. And in this case, there's not really, like, there's not treatment going on. This is an observational study, so there's no treatment happening. So C would not be the right answer. Placebo groups are only in experimental studies, and this is observational. And then D says it's an experimental study. It's not. So our answer is B. Good job. All right. Let's go to the next one. Okay. In the fall of 2015, there were a total of 508 undergraduate students enrolled in Penn State Shenango. Of these students, 204 were enrolled in associate degrees programs. So 204 divided by 508 is 0.402, which is equivalent to 40.2%. So that's 40.2% of all Penn State Shenango students were enrolled in associate degrees programs in fall 2015. Which of the following best describes the value of 0.402? No, that's fine. No, that's totally fine. I'm glad you guys come to both. Like I said, yeah, so our Thursday and Sunday sessions are the same PowerPoint, because, we do it in case people like miss Thursday or, can't come Sunday, whatever. But no, please answer. It's totally fine. I'm glad you guys came back. That means I wasn't horrible. So, okay, so yes, our answer is D. Good job. So like we discussed on Thursday, our sample always goes with statistic, S&S, and then our population always goes with parameter. So C and A aren't options because there's no such thing as a population statistic, nor is there a sample parameter. And then in this case, our 40.2% is a sample because it's coming from our population of 508, because these 204 were a sample. So in that case, it is going to be a sample statistic and not a population parameter. So good job. Okay, clear. All right. Alrighty, school psychologist wants to use students' intelligence test scores to predict their reading comprehension scores. She takes a sample of 100 students and records each individual's intelligence test and reading comprehension scores. In the scenario, what is the response variable? I'm just going to go over these just for, since we're recording this, and for people watching back on YouTube, what's up. So just so we have them on here. even though it's probably boring to you guys, but oh, okay, perfect. Woo! And a lot of people do come to both sessions, so it's totally normal. People find it really helpful because, and a lot of times, you know, if there are different people at each session, you know, sometimes people ask different questions at the end that like might be helpful to you. So it's very common, or you have different questions too. But yeah. So you want to take a guess on this one? On Blackboard, I used to be able to see when people were typing, which was fun, but now I can't see it on this one, which is sad. Okay, perfect. Yeah, so good. Our answer is C. So remember, our response variable is what is going to be our dependent variable. So it's going to be affected by our explanatory variable. So remember we talked about the word predict is important. This is going to be talking about, it's usually going to be our explanatory variable is predicting our response variable. So, because remember, explanatory variable is going to be the fixed one. That's our independent one. It's not affected, while our response variable is affected. So, in this case, I would say the intelligence test scores is going to be our explanatory variable because it's explaining what their reading comprehension scores is. Because you could change the word predict to explain in this case, and it would still make sense. It's the same idea. So you can say predict. I would say that also equals explain. So yeah, so B1, B right, because that's our explanatory variable. A is our sample size, so that's not right. And like I said, N is representative sample size. Just don't know if you guys learned that connotation yet. D is not true because just a relationship is not a variable, so that doesn't make sense. So that's not true. So C would be correct. That is a response variable because it is dependent upon the intelligence test scores, which is our explanatory variable. So good job. Okay. Next. Can't wait till I learn how to use this same thing. It'll be awesome. Okay. All right, last one. So our research question is, can the age of a child in months be used to predict his or her vocabulary? So data were collected from a sample of 500 ranging in age from 12 months to 60 months. What is our explanatory variable? So kind of the opposite of the last one. We're looking for explanatory variable. Yep, great job. It is A. So remember, explanatory variable is explaining our response variable. So remember, predict. This is an important word here. So we could also use this as explain. So if we say, can the age of a child in months be used to explain his or her vocabulary, that kind of gives us the hint that our vocabulary is going to be a response variable because that's what's being explained. So that'll be dependent upon what is before this. So age is going to be our explanatory variable because that's explaining the vocabulary. How old they are is explaining the vocabulary. And you always want to think about it logically, you know what I mean? Like someone who's older is going to have a different vocabulary than someone who's younger. So, you know, vocabulary isn't going to affect age. You know, you're not going to, how much someone's vocabulary isn't going to decide like how old they are, you know. So that's, think of it logically, you know, just after, that's one important thing in statistics is after you get your answer, think about it and be like, does this make sense? Because statistics is like, this is all about things in our world that we see every day. So just think about it and be like, does that make sense? So if you chose like vocabulary as your explanatory variable, be like, okay, does vocabulary explain our other variable, which is age? I always pick out my variables first, you know. So in this case, the way I would have done this problem is see like, what are my variables? And I would list them, you know. So I'll see we first have age, and then we have vocabulary. And then we want to, and then, you know, our sample size, I write out everything that I have first. Our sample size is 500. So that's all the information we're given. And then I want to go through here and say, okay, which one's explanatory, which one's response. So Okay, so is our age explaining our vocabulary, or is our vocabulary explaining our age? So if our vocabulary is explaining our age, that would mean that if someone has a vocabulary of 500, that like is affecting how old they are, which doesn't make sense. So age must be the explanatory, because that's affecting what the vocabulary is. How old they are and how much they've learned is affecting it. So that's why it'd be A. This is our sample size, so that's not right. This was our response. That's what we found out. And then the range of ages is just not relevant in this case. Our answer is A. Woohoo! Good job, guys. Very good. You're clearly learning very well. Okay, so like normal, we'll post these group reviews onto YouTube, so you can watch them as many times as you want. Listen to me drone on, and it's super fun. And our next group review will be on Thursday, and that will be for our next lesson, lesson 2, describing data part 1. So I got all your emails and everything. If you guys have any other questions, let me know. If not, you guys can have a good night, and we're good to go. All right, cool. I'll be here too. I hope. No, I'll be here. Don't worry. I have to show up, so. Good night. You have a great night. You're welcome. You have a great night.